All right, I'm going to talk about two easy applications of the dot product. The first one that I'll talk about is not this one, is this one, how to calculate projections. So if you have a vector, just goes down, if you have a vector u, right, and another vector v, a little longer maybe, and you want to project the vector u onto v, so this is the vector you're looking for, right? Imagine that there's sunlight or some light source down exactly, and this would be the shadow that is cast by vector v, u onto vector v, right? So the wording here is kind of important. It's the projection of u onto v. The order matters, and when you write it down, you got to write u on top and v at the bottom. So this vector is written as projection, sometimes lowercase, sometimes uppercase, doesn't really matter much, of u big onto v small. So the one at the top and the one at the bottom. So how do you even calculate this vector? It's not super complicated, okay? What you want to do is you want to, first of all, decide the length this thing is supposed to have. You can sort of prove this pretty easily. And if you look at the angle theta between the two vectors, right, this length has something to do with the cosine of theta, right? This length has something to do with the cosine of theta. The cosine of angle theta will be the magnitude of u, the magnitude of the projection of u into v divided by the magnitude of u adjacent over hypotenuse, SOHCAHTOA, right? And this gives me immediately for free the magnitude of the projection, how long it needs to be, right? So then what I do is I take vector v, divide by its own magnitude, right? So that means the magnitude of the projection. Let me write this down so I can finish my reasoning. And then to finish it up, the projection as a vector, not just as its magnitude, will be found by me taking vector v, right? Then what do? I divide it by its magnitude. That now has magnitude 1, right? Because it's v divided by its own magnitude. And now I multiply by this to get the correct magnitude for the projection, right? You see that? So this would be the correct formula, but then I go and just multiply by magnitude v and divide by magnitude v, because when I do that, these two together become at the bottom dot product of v with v, right? Magnitude squared. And at the top, all of these three together, not all three of them actually, not all four of them actually, just these three, right? V is going to stay, but magnitude of u times magnitude of v times the cosine will be the dot product of u times v, like so, and then times v. I think this formula is kind of complicated to prove. It's not terrible. I've proved more complicated formulas on the board in a calculus class, but the whole idea here is that it's super simple. It's uv divided by vv times v. So it's one u because you're projecting u onto v, and then a bunch of v's, right? uv over vv times v. It's pretty easy to remember in my modest opinion. And then the example that we're going to solve, let me move this down a little bit so I have space for the example, will be just find the projection of that given vector there onto v. It's this guy. So I just got to do u v times v divided by v times vector v. So what will I get? I will get u dot v, that would be -1 times 12, so -12 plus, all of that is at the top of the fraction, 4 times 1, so 4, and then 8 times 2, so 16. That is the top of the fraction. The bottom of the fraction is v dot v, so it's 12 times 12, 1 times 1, and 2 times 2, so 4. And then all of that times vector v, which is 12, comma 1, comma 2. So again, right, you're taking the direction of vector v and multiplying by the correct number to make the length match with the orange length their vector there needs to have. And then the rest is just algebra, business as usual, right? So this is 20 minus 12, 8 over 144 plus 1 plus 4. So that is going to be 1, is that 169? Well, of course not. Crazy. It was 149. Again, I'm forcing things a little bit to make it look, maybe have a root or something. I'm overthinking because this is the absolute value of the module, the magnitude squared. Getting tired too, so it's totally fine if you stop here. Totally fine. Yeah. But also it's fine to multiply these in and get 8 times 12 over 149, comma 8 times 1 over 149, comma 8 times 2 over 149. Totally fine also if you want to have your answer as a vector. Totally okay, right? So that's going to be 80 plus 16, so 96 over 149. I'm not even going to bother simplifying because I know I'll make a mistake if I do. That's fine. Okay, so that is a new vector. It is parallel to vector v because we got it by multiplying v by something, right? And it has the correct length to make it the projection of u onto v. That's a cool application, okay? It's the first application that I wanted to show you in this video. And now let's go about the second. The second application is work. So whenever you have a force that's applied on an object that moves from point A to point, from point P to point Q, or the letters that I'm using. Let's say you have point P right here and point Q right here. Generally speaking, in physics, the work done will be the force times the displacement, F times D, right? Generally speaking, if the force is parallel, right, let's say 100 newtons or something in the direction of the displacement, but if that's not the case, if the force that's applied is a vector in the wrong direction, right, so not necessarily parallel, then you have some angle here. What you would have to do theoretically would be to project the force with a cosine, right, of theta, get the correct direction of the force, and then multiply that by the displacement. But this projection is captured by making all of this a vector, not the left side, the right side, the force as a vector, and the displacement as a vector. Again, remember that there is a cosine involved in the right-hand side of this green formula I just wrote. Right, so you can also I use capital D here, but I can use lowercase d also. It doesn't really matter. It's just work is force dot product with the displacement vector. So pretty easy. Okay, so this is pretty helpful in physics. Now, we have a tow truck. Here's the problem we're solving. There's a tow truck that's going to drag a stalled car along a road, and it makes a 60, the chain of the tow truck. Right, so there's the stalled car, maybe. It's great at drawing cars. You guys are going to be amazed. And there's, so the light's off, I guess. And there's the truck here, even better at drawing tow trucks. Yeah. Awesome. And there's the chain that connects the two that's making a 60-degree angle. Oh, it's kind of small. It's a 60-degree angle, right? With the horizontal, with the road, I guess. And the tension on the chain is 250 newtons. So I don't know if I believe it, right? Gotta move the car, be accelerating really slowly, but hey, it is what it is. So the force is it a vector, right? The force is a vector. Is the force equal to 50, right? No, because that's not a vector. That's just a number. The force is some vector that forms an angle of 60 degrees with the road, but the displacement vector will be, we're pulling the car 450 kilometers, so the displacement vector, lowercase d, uppercase d, doesn't matter. It will not also be 150, but it will have magnitude 150, just like the force will have magnitude 250. Okay? And we know that the angle between them will be 60. So to calculate the work, that will be F dot D to be magnitude F, magnitude D, times the cosine of the angle. So it will be 250 dot 150 dot cosine 60. So it'll be 250 times 150 times 1/2 the cosine of 60 degrees. And I wonder how I want to do this. It's fine. It's not bad. 125 times 150 is not terrible. I'll do it here. 50 times 12 could have been worse. Times, see, messing it up already. I gotta be careful. 125 times 15. 25, 2, 10, 2, 12, 5, 6, and then 1, 2, 5. So 5, 7, 8, 1. So this will be 1875 with an extra 0. Let me check my calculator, just so this video isn't a source of shame forever. No, this is fine. So this is 1875, and I gotta be careful because we want the answer in joules. So joules are Newton meters, right? So maybe I should have changed this to meters by adding a couple more zeros there. Newton times meter makes a joule. So a joule is a Newton times a meter, lowercase m there. So I should have changed this displacement to from kilometers to meters. So we're going to do that now. In hindsight, it's not going to be a problem because 1 kilometer is 1,000 meters. So just add 3 zeros there. So this will be 1,000, count the zeros, 18,750,000 joules. I'm only doing that because the problem told me so. The problem told me it wanted the answer in joules, so I'll leave it like so. If I did not, if I were not told to this by the problem, I could have said the answer was simply 18,750 kilojoules. With just sort of transform these extra 3 zeros into a K, right, for kilo. But that's fine. That should be your application for this video.